So let me start with this presentation. And this presentation is basically going to talk about like stack and like how they do with like opcat. So I will talk about 4 things. First of all is to give some background on stack. And then I will talk about why opcat would be like important for like stack to work. And like why it would be very difficult if you don't have like opcat. And the last point will be about that like how do we kind of implement this like stack proof verifier. Okay, so we will start with like the background of like stack. So I think the first point that I want to make is because that like I think ZK still have a new things like for the like Bitcoin people, because like most of the like basically Bitcoin have worked on ZK, but that's kind of like only early 2 years. And later on, like Bitcoin have never really get touch of the ZK. Well, at the same time, ZK actually have developed it like quite a lot. So I think one of the reasons why people have been skeptical about ZK rollup or ZK layer 2 is because that people think ZK is actually a relatively new technology that is probably not like stable enough to be used. But ZK is actually something that is like pretty well studied, like and have been used like for Ethereum layer 2 that actually allow the access on like Ethereum ecosystem that is now secured by ZK. Or in other words, is that if ZK is broken, those like assets will be stolen, but they have been running safely for quite a few years. And privacy payment have also been using ZK. And this actually have been battle tested for at least 5+ years. If we count privacy payment, like that would be actually have 8+ years. This is even older than like SegWit. Okay, and one thing that people might be wondering is that, okay, even if ZK have a long history, but a lot of the ZK algorithm that you are using are kind of recent. But like, and people will wonder whether or not this new algorithm is kind of like stable enough, have they gone through enough testing. Here I want to use this slide to kind of show you that like, all the new algorithms are actually kind of belong to like our knowledge about ZK system in general a few years ago. This is a slide from 5 years ago. And this is basically a slide at that time that have classified different kinds of the ZK proof system and put them into like table and category. And here, what an interesting thing is that like, you can basically do all the, wait, is this one okay? Okay, but basically is that like all the ZK algorithms are basically belong to 3 different families. You can basically classify them. And like, and even 5 years later, this like classification still work. There's no algorithm that fall beyond like this table. And all this table, and this table basically are talking that like you can actually, all the ZK algorithms are being built up by small components. And if you apply a compiler onto that, you compile it into like, let's say a ZK proof system. And here I have basically 3 compilers. Compiler A, like from compiler A, we actually know one algorithm that is like quite popular, Grok 16. And from the name, you can guess that is from 2016. Compiler V actually give you like Flonk that is like currently BBM is testing over. BBM also is working on Grok 16. Compiler C is like, it's the one where like all the stack and like stack related like system are based on. And still today, these 3 compilers are still the way that people get ZK system like here. Okay, so now I will kind of like just give a very quick like introduction about ZK. The idea is that like, so how ZK works is like this, is that like you have like statement that you want to prove, you convert them into like a number of the like polynomial, and you want to check that this polynomial will satisfy some relationship. And I can show you a very simple example. Let's say that you have 3 polynomials, A, B, C, and you just want to do a very simple test that like A times B equal to C. What like will be happening in Stack is that like Stack will commit this polynomial, and by commitment, here is a very specific way, is that you just evaluate this polynomial on a bunch of the points, and then you kind of just like put that value evaluation onto like a Merkle tree. And you have to commit all of that. And like here, I use a number omega. Omega is basically what we call group generator. And it will just be a number. And you are basically evaluating the polynomial over the powers of these numbers. And here I talk about like the degree. 2L times D, 2 to the L times D. D is like the degree of the polynomial AVC that you are committing to. L is a parameter that is mostly for security. But basically is that if you are committing a polynomial of degree D, you don't just commit that, the commit actually an extension over that. So you are committing more points than what is actually needed to recover the polynomial. And so the commitment of a polynomial eventually will just be a Merkle tree, will actually be the root of the Merkle tree. And like on the leaves of this Merkle tree is basically just evaluation of A and AVC over like those points. One thing that I want to point out is that like you don't actually need 3 different trees to commit A, B, and C. You can commit them on the same one. Like you have one tree and you put and each of the leaf will be evaluation of A, B, and C put together. Okay. And back to the stack is that like, so what stack do is that like you now have those polynomial. What I want to show is to check whether A times B equal to C. And there's a mathematical result actually tell you that if you want to test that, you can actually test that on a random point. Like basically that, let me just find a random value. Okay, let me check whether on that random value, ABC will equal to that. And if it is, with a very high possibility, this will be true. And all you need to do is, let me kind of point out here, is that you just need to make sure that like this random number that you are picking is from a sufficiently large space. So it's kind of really random. And then what is the rest of the verifier job is to, it basically is to test that like, test a specific polynomial to be low degree. And why is this step necessary? Here is the problem, is that like if you look at the first paragraph here, the evaluation on AVC is not from the Merkle tree, but is provided by the prover. Like prover just tell the verifier that here is the value of AVC on that specific point. Verifier need to verify that, need to make sure that that is actually the evaluation on those points. And what the verifier do is basically to show that. So this is like actually there should be a randomizer there. But the idea of this like polynomial is to show that like if A on zeta actually evaluating to the value that like the prover provide, then this will be a low degree polynomial, otherwise it wouldn't. And you can do the same thing for B and C. I should actually adding a randomizer before the term of B and the term before C. But like you kind of get the high level idea is that if this is a polynomial, it means that like the value that prover provide actually match. And this will be done by using like the leaves of the Merkle tree. And remember the Merkle tree that we present here, but basically that in stack, what you do is that you just randomly select a bunch of the leaves and check and run what we call low degree test protocol to check whether like the polynomial here, T, actually is a low degree function. Okay. And that is kind of the idea of like the start. And like, well, I only give very high level idea because I want to use that to just to tell you what would be the component of a start verifier. You will have 2 parts of that. First of all, you will do a bunch of the operation over the finite field. Second thing is that you will be opening the Merkle tree on a bunch of the leaves. And this is actually all the overhead of a start verifier. And this actually is a good size that like when an algorithm is simple, it kind of means that he have been kind of studied for a while. It's kind of quite, I would not say elegant, but basically that like he actually follow a very specific way to construct the protocol, and that like it wouldn't be kind of too complicated. Okay, and the second point I want to mention, and probably this is why you do need OPCAT to make start proof verification efficient, is that like there are 2 reasons of that. The first one have to do with the Merkle tree. For like start protocol, you have to use Merkle tree. There's no alternative for that. And without OPCAT, like Bitcoin, although Bitcoin have like hash opcode, they are not very useful. Like you cannot just use the hash opcode to do the hashing. You have to write your own SHA-256 implementation in Bitcoin opcode, and that can be very like inefficient. But with OPCAT, you can do that very easily. And here I actually have the code. Well, it kind of was written in a little bit pseudocode way, but this is the actual Rust code that is being used to generate the script to do the like Merkle tree. But it's actually very simple. What happened here is that like the OP key is a pseudo opcode. It basically pulls an element from the stack. And all you need to do for Merkle tree is that, okay, is this one the left element or the right element? If it's left, I will switch the order. That's what this line is doing. doing a conditional swap of left and right. And after swapping, I do an opcat, and then I run the hash opcode, which here the hash will be run by, it will be converted into 12 to 56. This will allow you to do the compression as required in Merkle tree. And you basically do this for every layer of the tree, and you end up just comparing whether it matches the Merkle root hash that you are provided. This is a very simple code, and you don't need to touch the hash function. Don't need to really emulate the hash function. This is reason one. Another reason why opcat can be very useful is that opcat gives you recursive covenant, and that can allow you to split execution into many smaller transactions. And this will be very useful because if you have a transaction that is large, although it can still be put into one block, meaning that the script will be smaller than 4 megabytes, there's still some problem. First of all, you cannot easily submit this through the P2P network. You probably need to work with some mining pool that actually accept non-standard transaction. If you do with slipstream, the only problem is that there will be a double fee. They basically double the fee that will be charged for that. Another problem is probably more from the network perspective is that if you always have big chunk of the transaction that might take almost the entire block, they might actually they will affect the user experience. And I want to explain that a little bit more. Because people may ask me that, okay, what would be the differences? Because if I have smaller chunk of the transaction, and I put them together, would that really affect the user experience that differently? That actually has something to do with queuing. Why? So I actually can use a simple example. Let's say I'm in Disneyland. There is a standby line and there is a lightning line. Lightning line is where people pay to go quicker. There are different strategies to decide the gas because usually the standby line and the lightning line will both have gas. Some of the gas pay more, some of the gas pay less. There will be a strategy on by the cast member to decide how many standby gas will go to the next round of the show, how many from the lightning will go into that. And there are clearly different strategies. One way is that, okay, if there are lightning gas, I always let them in first. This might cause a problem is that if there are so many lightning gas, standby gas will not move forward at all, right? This is exactly the problem for a large block, is that if a miner say there's a large block, I want to accommodate that, all the transactions that are pending will have to go to the next block. But if you allow some transactions to go together, the average wait time will go down. And why? Why is that the case? Because you need to know that for Bitcoin transactions, they come and go, right? All the transactions probably coming at a specific time. And what really affects the user experience is that when I send out the transaction, how long it takes to get it merged. And it has to do with the strategy, how you handle this. And if you can split the transaction into smaller chunks, the wait time for non-big transaction will actually go down. Okay, and opcat can have recursive covenant. And so you can actually, so if you have big transaction, you can also always slide it into smaller chunks so that all the block can still carry out something. This is also useful because unless you really want your big transaction to be settled in one block, otherwise this will also provide more flexibility. Okay, and the good thing here is that each of the transaction after splitting is all small enough so that you don't need to use slipstream. All the miner will accept that. This might be actually better than using slipstream. For slipstream to work, you need to wait for Marathon to mine the block. But for this to work, you probably just need to wait for the next one. And that, as I mentioned, it doesn't affect other transactions that much. Okay, first of all, I probably want to pause here. Any questions so far? Okay, let me move forward. So the next thing is that opcat give you a very powerful primitive. You can do optimistic ZK proof verification. But the idea is this: is that okay, let me talk about what optimistic ZK verification means. But basically, this is that now if you want to do the entire ZKP verification of Bitcoin, there's still a cost for that. You would still probably, I would say about $1,000 in US dollar to do the proof verification. There is another way to do that, is that okay, let me just post the proof. And if in the next 5 block or 6 block, someone see this and say that this proof doesn't look right, I want to like kind of show that it's wrong, so that like, I can kind of like just like I would say it's a little bit more like for proof is that you post a proof, and if 6 blocks later nobody can challenge that, then I assume that this proof is correct. And this is not really a new idea, because in Lightning Network, you rely heavily on watchtower, who can see transaction on mainnet, and if something actually is wrong, watchtower are responsible, and they need to act fast enough to kind of say that like, that transaction is not right, let me prove that it's wrong. So we can also do something similar here, is that I will post a proof verification, and if nobody is going to challenge that proof within like a certain period of the time, we will assume that this is correct. But because it's on Bitcoin, so everyone can see it, and you only need to require like global watchtower. Opcat can give you that, and this have a few benefits. First of all, with Opcat, it will be much simpler to than like BBM to do the for proof. It's 0 round, like it will be very easy. Basically, you post the proof and you just wait, sit back, and relax at home. Like some verifier will figure out how to deal with it. And if the proof is valid, there's basically no cost at all to do this. Like you post the proof, nothing will happen because it's not challengeable, because it's correct. Then you can just move forward with that. Okay, now I will talk about why you cannot easily do that with Opcat. The problem is this, is that if you don't have Opcat, I think actually the bigger problem is that if you want to do general purpose computation, like for example using BBM, data availability is going to be a big problem. So in BBM, you need to make data availability, and they also need to be done in a very specific way, so that they are what I call challengeable. That's that if the data you post here is being shown to be not correct or inconsistent later on, I can slash the operator. And the problem here is that like if you want to make like data availability that is changeable, we only know one way to do that. That way is like this, that first of all, you need to commit the data, and the only way that we know how to do that at this moment is to use like Lamport signature or Winterny signature. That have a cost. Like, and also is that, okay, this is a cost, but that like, you cannot commit too much data using that, because you will need to post that data elsewhere. So people usually will also use like Merkle tree or something, or like just use hash function to compress the data. But you basically need to do these two things in order to commit the data. And the problem with that is that this will be very heavy, especially in BBM, is that like, so in BBM, this is also an issue, is that if you ask the operator to provide all the data, this can be actually extremely heavy. That might actually ruin the benefit of BBM. So in BBM, what it says is that, okay, we will do this, but only on demand, is that if someone challenged that, I will post the data, and this person who challenged me will need to pay for the data publication fee. And that's not the idea in BBM. So this is like, but what I want to say is that without Opcat, you actually don't have a lot of the way to do like challengeable data availability, and every bit will be very expensive. And that like, and this is like even worse for like Start compared to Block 16. Start need to post a lot of data, so that it will actually require much more DA for that. BBM now, they actually have a progress. I will not be the person to talk about that. Like some other company will probably talk about that like in the incoming months. But basically that like that is a way to do BBM DA more efficiently. But that like Start still suffer from that. Is that Start still will suffer from like the difficulty of DA without Opcat, but it's now possible. So Start will and us are kind of also working on like a BBM version of the Start verifier. Okay, but that like another company will probably present how they do like this like bone trick on like DA like later on. Okay, but with Opcat it's easy. Just create a Merkle tree and show people the root of the Merkle tree. That kind of complete the data availability. Basically that you have a script. In this script you just write out the data, and then you hash everything together and say that, okay, I publish all of this in a transaction so people know that. And this is challengeable, because you post that, you can put that on the state, and people later will challenge directly on the state. The key part about this is what Opcat enable is that just by writing data on the like blockchain, because there is recursive covenant, you can challenge that. Basically, that it makes challengeable very easy, because you can always look back into the history of the blockchain, while BBM itself cannot use that because you don't have Opcat. And another problem about why, so this actually come back to the title is that, well, without opcat, why would that be very difficult is that now local tree also become much more expensive because you need to manually evaluate hash function. And that, like, the best result we know at this moment for manual evaluation for hash function is probably like 75,000 script bytes for hashing like 64 bytes. And that's from like Blade 3. And another limitation with our opcat to do this general purpose computation is that like it's not easy to parsing data. Like in big VM, you probably know that the execution will be split into a lot of the chunks. The problem is that if you want to pass data around this trunk, so with opcat, you actually have some very interesting design that you can even build key value storage easily. And that like you can actually use that very cheap, so you can just pass the data any way you want. I will show this example later on, but basically that like we can actually write Rust code and that like we can actually abstract this memory primitive and you can use that if you want, like when you are writing the script. But if you don't have opcat, you can still do that. It would be very heavy. You will need to use Lamport signature and Winternitz signature to do that. And you also need to use manual hash function as I mentioned before. So this is kind of the problem that like without opcat, yeah, you can still do all of this, but it will be very like complicated. Okay, I will end this call by just giving you some of the like highlight about like our implement the start proof verifier. But like a large part of this will be about our like domain specific language on how to write like start proof verifier. So you can also do that your own. Okay, we do like a Rust based like DSL. Like in Stack, you will actually touch a few of the like what we call like data structure or like few element. You can actually just define them as regular Rust like structure, and you can build that like step by step. Like for example, in start proof verification, we have something called M31. It's basically a number in the finite field by a prime number. You define that, and when you are going to do the few extension of the element, you can also easily build that just using Rust to do the composability. You can create what we call the complex extension of M31 by just have like the M31 element as one of the struct, and you can basically use that to construct the complex extension. You can do the degree 4 extension by extending from the complex extension. This allows you to represent the data that is in a way that is composable. And if you want to do addition, like when we want to write the script to do finite field addition in Rust, what we do is this: is that you write a more complicated version for M31. Later, when you are doing the complex version and also the degree 4 extension, you can just build over that. Like for example, here I write the code. It's actually also not a lot. But when you are doing the complex extension, you will just say that, okay, how do I do the addition? The imaginary part will be added by the imaginary part. The real part will be added by the real part. Okay, that complete the complex extension addition. Degree 4 extension is done by adding the first part with the first part, second part with the second part. So I can also similarly implement that. This allows you to reuse as much code as possible, and you can kind of build up the basically complicated function from smaller function. And all this is done by using Rust. You don't need to write a separate compiler. They are actually just like a wrapper using over Rust. Okay, and when we want to finally get the script of the program that we write in DSL, it's actually quite easy. In the previous code, actually there's something called CS. And the operation that you've done, for example, here when you insert the script, CS will actually store the script information. And at the end, you just use the compiler to run over that script. You will get a structure, what we call compile program. And inside it, that's the script. And that will be the Bitcoin script. So basically that this DSL allow you to write the entire program almost entirely in high-level language. And eventually you compile it give you a Bitcoin script for the entire thing. Okay, and you can actually use this to write high-level code very easily. For example, here is one specific stack on the start proof verification. On the right is what actually happened. What do you want from it? And the left is basically the code. And actually this can be written even easily. For example, I can merge the line with the div to the next line. But this is how easy it would be for you to type write the code. You can write it almost like you are writing like regular Rust code. And another example, this one is a little bit more complicated, but as you can see from the right, that's kind of the code that's actually being executed. The Rust code where kind of, I would say, is clearly not entirely the same with like you write the Rust code directly, but you can say that like it's become much more human readable, and you actually see no Bitcoin opcode here. And this code will actually be like the compiler will actually generate a very like comprehensive script that have to do all the operation. And that we also build a database abstraction that I showed previously. You can, like here is basically the code where you want to compute some coefficient. What you do is that you read the data from, like here is basically like memory, and then you finish the computation, you write them back. And this number that I read from the memory is done from previous like execution. And after like my execution, I have the data. They will be written and they will be used for like future execution. And the only addition step that you need to do, like for using this memory abstraction, is that you need to initialize that. When you have your script, you initialize that at the beginning, and you have like save the memory at the end. And you only need a final step to do like what we call memory checking. You only need to do that once. Okay. And like I will end this talk by just showing you kind of what is like the transaction or like the workflow of our like step like verifier. Like I'm not going to explain each part of it, but the script will be actually split into like a lot of the like smaller chunk of the like will be split into a lot of the small chunk. Actually, each of the like chunk will be pretty small. None of them is like, I think none of them is larger than 100,000 like bytes. We just want to make sure that it doesn't impact the blockchain as much, and we want to make it easier to design. It will run a few like steps to do some computation, and then it will go to what I would say a circle. That you were doing like the A transaction inside this circle A time, and finally it will go to like the cleanup. And after cleanup, you can do other things. You can, for example, because you have the slide, you want to use that, right? For a roll-up, the anything else will be the one that settle layer 1, layer 2 token like exchange or something. And you can also start a new proof, like just verify the next proof, like from here. But this is basically like the steps, and you can find the code for each of these like steps together. But we can split the script, and here actually we split that kind of manually. You split that based on the meaning of that step. You don't like have to really figure out that okay, or automatically generate that. It's actually also easy for you to just split the step based on that utility. Okay. And that's basically the code for it. And this actually kind of involves some detail about how the proof system actually works, but that like you can always find them on the code. Yeah. You have a question, right?
Yeah, I can wait till that.
Okay. Anyway, like the end is very quick. So we have the GitHub repo, and we also have a Telegram group that if you are interested, you can join. Yeah. I think if you have a question, I need to give you the microphone, right?
Sure.
Oh, yeah.
Great. Thanks so much for the talk. This is a bit more basic. It's about on the Bitcoin side and getting the transactions included in blocks. And basically, I'm curious, like because I think in the previous talk you had to deal with constraints on in the mempool, like the limits on ancestors and descendants and the size per block. So I'm wondering how, if you're working around that, how you're doing that.
Oh, this one actually still suffer from like the same limitation. But the solution for that is like this. So what would be the like that's so this actually haven't yet used that technique to bypass the limitation. But the way to bypass it will be like this, is that here I actually kind of submit the transaction kind of sequentially, right? You have the step 1, you have the step 2. You think the step 2 will depend on the step 1 transaction. The way to bypass that is that you run this transaction separately. Is that step 1 will be one transaction. Step 2 will be also an independent transaction that actually have nothing to do with step 1. But step 2 will be basically saying that I claim this to be my previous state, and I claim this to be my after state, and I will show that like the state transition is correct. And it will actually not check what the like transaction 1 is doing. Like basically that after all these like steps are being completed, and each of them were, how we say that they are logically depending on each other, but they don't depend on each other from the transaction flow. Like they don't consume the previous one's UTXO output. You have the final, basically that after all of this is being executed, you have one single transaction that basically loop back into the blockchain to check that, okay, step 1 is present, step 2 is present, and the step 2's like input match the step 1's output. Basically that you will defer to the final stage when all of them are being settled, and then you start to checking that. The benefit of that is that because the mempool is not aware of that connection, they will treat them as independent like transaction, and therefore the descendant and ancestor limit will not apply to them.
Got it. Thank you.
Yeah. Let me pass by the mic.
Yeah.
Sorry. Go ahead.
Thank you. Just a kind of question on your personal perspective on OPCAT and like, is it going to happen? When it might happen? I mean, as someone who's spending a significant amount of time and research in this area, how do you kind of evaluate that? You know, the risks involved in that, and yeah, how do you kind of what's just sort of your personal perspective on it?
Yeah.
Thank you.
So first of all, like the risk for me is actually kind of not too much. Why? Because like Star will give us a grant, so that like, and it's not like, oh, if OPCAT eventually didn't move forward, I am wasting all my time on that. Like I think like so far based on basically I talked with like some like people, some of the core developer. I think what happened with like Bitcoin history is like this, that we have two like big changes to the protocol, right? Segway and also like Taproot. Both of them have a little bit of their own unique history. So I think it's a little, I would say OPCAT is, wait, only 2 minutes. Okay, OPCAT is a little bit like this, is that like, if someone push for that, and that a lot of the core developers start to review that, it might actually happen very quickly. So I would say that there is no set timeline, just need people to add on that. Because one thing that was actually show up in a like informal discussion yesterday is that, oh, did we already submit a PR for merging OPCAT to like Bitcoin, basically the like Bitcoin core? Actually, yes, it was several months ago. People forgot about that. You can actually ask the core people to review that, but reviewing that will mean an endorsement. And so I would say that the actual engineering part of merging OPCAT is actually something that probably can be done in 1 day or 2. Like what is like really missing at this moment is that like what is the strong incentive to do that today? It's a little bit like something you can always procrastinate. And that like Bitcoin history, if you look at Segway and look at Taproot, they are also kind of like, they, as I say, is that they still have their own history of how it eventually happened. OPCAT probably will not follow the same way, but that like, I personally think is that like, this is probably not harder than we thought. Yeah.
Do you think that it might be easier to activate OPCAT on another chain that is like derived from Bitcoin, like or something similar? Like in some ways, Signet for the Inquisition serves that, but there's no like real assets there, so you may not get like the similar incentive to kind of vet out that like these. You know, this actually like proves out while we are waiting for like core devs to approve it.
Yeah, I guess I might be running out of time, but I think, so Signet already have that. Fractal is also a Bitcoin fork that kind of try to do that. I think really the main thing is that like, well, why do we do that on Bitcoin? Have a lot to do with like Bitcoin itself. I think it's not just the chain, it's more about like the token value and a lot of that. Is that Bitcoin is still, you think about that, Bitcoin is the biggest asset like in the like blockchain ecosystem. And people think you can actually build a lot of the application over there. This is actually kind of similar to the question is that why it didn't have all those things, right? They can also be done on a different chain. So my perspective, and I think it's a reason why a lot of the people, even a lot of the investors, they really like Bitcoin is that if you look at just this like macro like data, like, okay, how much is the Bitcoin total valuation? How does the Bitcoin performance throughout the year? Is it a lot of speculation or they actually have a stronger support? Bitcoin is like more positive on that side. So kind of like, it's kind of like people thinking that like Bitcoin seems really good from different perspectives, including the token. And that like we can do, basically if you want to build something, Bitcoin might be a better like ecosystem for you to do that. Yeah. Okay, I think we need to do the next. It's the next talk, right?
Yeah.
Okay.
Thank you. Thank you, Weikeng.